All right. Well, good afternoon, folks. Hopefully everyone's okay. Let's continue on with where we left off with yesterday. With one quick note, let's go ahead for the homework tonight. Finish up the second part of the practice packet that I gave you, the second practice kinematics practice packet. And so please make sure you get that done. And then I'll try to post the third packet for you that gives you a chance to practice what we've done up till this point here with acceleration, interpreting velocity time graphs, and working out these acceleration problems. I'll try to post that by this afternoon. If not, I'll get it posted for you tomorrow, and I'll assign some practice for you to do over the weekend. Let's practice this and try to get it done, okay? And then come by and see me if you have any questions about it, okay? All right. What we have to be able to do then is, like I said, if we don't have graphing, if we don't have access to a graph, can we still, based on the information that's given to us in a problem, be able to make predictions about what changes will occur if you're given a set of data points? If you're given some information, can you tell them? Can you predict them? What will happen with these changes here? And the answer there is that we should be able to, if we are given. Sorry, let me go ahead and start this here. If we are given information, we should be able to interpret that data, and then we should be able to take what we know and make some predictions about it. That's what you need to be able to do moving forward, folks. We need to be able to use the formulas that we derive from the graphs. And remember, the graphs are very useful, first of all, in helping us to organize the data, and it helps us to predict by extrapolating or interpolating the graphs. We can predict data points. We can get data points that are outside of the set of data that we originally collected in order to graph. So we can use graphing for that. But graphs are fairly cumbersome to use. You have to be able to have the graph, you have to have a picture there all the time. And so what we need to be able to eventually, the end goal for graphing is to come up with a relationship between all the variables that are part of that graph, and be able to express that relationship in a simple formula. And that's the goal of physics. And now with physics, the formulas aren't always simple. They won't be simple like the ones we have here, but that's the goal. Be able to obtain the information that's organized in graphical form, and obtain then a formula that summarizes all of the relationships that are expressed in that particular graph, and then be able to use that formula to make predictions in much the same way that we can use the graph to make predictions. And so that's problem solving. That's problem solving. That's what we started doing yesterday, and that's what we will continue to do today. And make sure you understand, as we move forward and we use the kinematic equations, and when I introduce them to you, they're basically formulas that were obtained from graphs, and with the kinematic equations that I'll present to you today, they are derived from other formulas. I won't do those derivations for you. Those derivations, and I'll point this out when we get to them in just a moment. You'll get plenty of opportunities to derive those equations in physics. And for those of you who have already taken physics, I think Sansaloni's probably gone over that with you, how you derive those equations. But understand then, many of the equations that we work with are derived equations, meaning then that we set them up ourselves. Okay? These equations then are these formulas, derived formulas. These formulas that we come up with are basically taking other formulas, combining them together, and coming up with a new formula that we can use to make these predictions. So formulas then are initially they are taken from graphs. They are taken from data that we can use and patterns that we observe with that data. But then what we do then, and this is more as we advance in physics and we advance in science, and especially the physical sciences, the formulas that we work with, that we use to make predictions with, end up being a result of combining together other formulas. And so this process of deriving equations you need, this is a skill that you need to be able to develop if you haven't done so already. For those of you who will be continuing on with us here at school at Bishop, and if you take me or Sansaloni, we will work on that. I think in your math classes as well, they work on deriving equations, but you have to be able to do that. Okay, so the equations that we're going to work with, that you will need to solve the problems, won't always be as simple as the one that we use to solve this problem here. So this problem here, we just simply took the formula for acceleration. We plugged in the values that we were able to identify. We identified what was known. We identified what they want us to solve for, which is our unknown. We went ahead and chose the correct formula that we would need to solve for that unknown. And if we needed to rearrange the variables to solve for the unknown here, we did not have to because we were asked to solve for the acceleration. And then we plugged in the numbers, plugged in the known values, and solved for our unknown. So that's the process that we use to work through these types of problems. Now this problem is fairly simple, and I know it's fairly simple, but let's work on the method to solving problems using simple problems first, and then we can deal with more advanced problems at a later time in a later class. Okay. All right. So with that said, then moving forward, what we need to be able to do then is we need to be able to obtain a formula. We need to be able to make predictions. Okay. So I hope you remember this here. So we interpreted this. So this was a velocity time graph that we worked with a while back last week. We have velocity and time here plotted for two different objects. We were able to calculate for the acceleration of the object represented in blue here. And what we did then is we took that and we were able to, based on the acceleration, we saw that it's constant acceleration. We saw then that each time interval here, the object is accelerating at a rate of 5 meters per second squared. That's constant, which means then that the acceleration does not change. But what does change? The velocities do change. And we saw then here that with the velocities then, as we go from, say, 0 seconds to 1 second, the velocity changes from 0 meters per second to 5 meters per second. Again, constant acceleration means then that the acceleration does not change. But what it does mean is that the velocity is changing. And so we see then that the object is speeding up, obviously, here. We already talked about that. So that in the second time interval here, based upon the graph here, we were able to see then that the object starts out at 5 meters per second at the 1 second time 1 second time interval, and it increases to 10 meters per second at the second time interval here. And so we were able to obtain that from the graph as well. Okay. All right. So the question here is this: okay, what then would be the speed? And this is what I left you with at that time when we talked about this. That one question an interesting question that we should be able to answer, and that is, if we know that the object here is moving at a constant, has a constant acceleration, that means the acceleration doesn't change. And if you notice here, each one of these 1 second time intervals, the acceleration does not change; it is constant. Knowing that we have constant acceleration here, could we find the velocity at 3 seconds, okay, which is well outside of this graph here. So the graph here only goes up to about 9 seconds here. So it's well outside the graph. So we have two options. One is that we extend the graph here, okay, and then the other option then is to solve for it. And how will we solve for it? Okay, so again, two options here to answer the question. What is the velocity at 3 seconds? What is the velocity at 3 seconds for this for the blue object here? And again, this graph here, if you notice, extends well beyond the 3 second interval. The velocity here stops at 9. Okay, and this graph here extends onward. So we have two options: extend the graph here, and then extrapolate the blue line, or we can solve for it. I think of the two, solving for it is a lot easier, and that's what we're going to work with here, okay? Because we want to be able to work out these problems. And so in order to solve for this particular velocity here, let's go ahead and see what we can do in order to solve for it. Okay? All right, so let's write down what we know. So let's go through the process here and write down what we know, what we don't know, what the equation to solve for. Okay? All right, so we are looking at the velocity at the end of this 3 second time interval here, okay? That's what we're going to solve for. So what do we know? Well, we know then the initial velocity in this time interval here. So we're looking at the time interval between 2 seconds and 3 seconds here. Okay, so the time interval between 2 seconds and 3 seconds. So what do we know? We know the initial velocity at that time interval. The initial velocity then is 10 meters per second. Okay, the initial velocity is going to be 10 meters per second. Okay, what else do we know? So that we know right there, that's what we know. What else do we know? We know the acceleration. Okay, so the slope here represents the acceleration. We know that the acceleration is constant, and we know that the acceleration is 5 meters per second squared. So we're writing down what we know. And then finally, we know what the time interval is. Okay, we know the time interval is a 1 second time interval. So we know then that the time interval is a 1 second time interval. So we'll write that down as well. Okay, all right. And so that's what we know. Okay, within to solve for the V final here, these are the three factors that we know. That's what is known to us, that's given to us from this graph here. Okay, so what are we solving for then? We're solving for the V at the end of that time period, which we will refer to as V final. So we were asking ourselves then, what is that V final there? Okay, all right. So do we have a formula that relates all four of these factors together? And the answer is yes. We talked about this. Remember, we had the formula for acceleration. The formula for acceleration tells us then that the change in velocity is over time, okay, over the time interval, which is then V final minus V initial all over time. And so if you notice here, there's V final, which is what we're solving for. There's V initial, which is what we have right here. There's the time interval, which we've indicated right here, and the acceleration is given to us right there, okay? So this is the formula that we will need. Now, it's not quite arranged in the form that we need to solve for V final, so let's go ahead and rearrange the equation here to solve for V final, okay? So solve for V final, multiply both, we're gonna isolate V final by itself, so what do? Multiply both sides by time, so we get then AT is equal to V final minus V initial. Okay, that's what we have there. And then to solve then for V final, we're going to add V initial to both sides. And I'm just going to really quickly adjust this here. So that means then solve for V final, we're going to add V initial to both sides. And we have then AT plus V initial. This is what we refer to as a derived equation. Remember I talked about derived equations, equations that we would we can get ourselves from manipulating other formulas, other equations. And so what we did then was we rearranged this equation here, this formula that we know that describes acceleration. This is the formula that describes acceleration. We got that from the graph. You remember the slope here is what we got for acceleration. We took this particular formula, we rearranged it, and we solved for V final. That is the deriving an equation. So we derived this equation here that now will allow us to solve for V final. Okay, so let's go ahead. The last step then is to substitute in what we know. Okay, so we know then the acceleration, let's go ahead and substitute that in as 5 meters per second squared. Okay, the time interval, which is 1 second. Okay, and we're going to add that to V initial, which is 10 meters per second. Okay, so all we did at this point then, we're going to substitute in those values, and so therefore V final, when we plug everything in, is going to be 15 meters per second. Okay, so that, folks, is our final answer, and that's how we obtain that final answer. And I know that it looks pretty straightforward, very simple. For some of us, it'll be extremely simple, but like I said, let's start out simple. Let's start out simple, and let's work out these problems using simple methods. This idea, the reason why I want to do this is because if we're working out simple problems, it gets into your mind the methodology of which we would use to solve for these types of problems. Okay, all right. So let's go ahead then. Make sure you have that. Okay, and I want to go ahead and I want to work out another problem with you. Okay, but before we do, let's go ahead and let's take a look at. So that's essentially kinematics. What we just did there, folks, is kinematics, which is basically looking at motion in one dimension, okay, and so what we've been doing without regard to cause. But what we want to do then is we want to be able to simply describe how an object moves and be able, from that description, make predictions from it, okay? So we have been talking, and essentially what we've been doing is studying kinematics, okay? And so there are 3 basic kinematic equations that we're going to use. And if you notice here, I just derived this first one for you. Okay, and so what you're going to notice here, folks, is that with all the kinematic equations, these are derived equations. So all 3 of these, and there is a 4th one that you'll learn later, but all 3 of these kinematic equations are derived equations. We saw then that we were able to derive that equation from the equation for acceleration, which is V final minus V initial times time. Okay, so we took this formula here, which describes acceleration, we rearrange it, and then we derive this equation to give us V final. We can solve then, if for this particular equation, If we're given 3 of the variables, we can solve for the 4th. Okay? So if we were solving for v final like we did in the previous problem, we needed v initial, which we had. We needed acceleration, which we also had, we were given. And then the time. Here, time final, just make sure you keep in mind that time final is just the time interval. Okay? And so with that said, then we were given that as well. We can equally use this equation. We can equally likely use this equation. We can also use this equation to solve for v initial if we wanted to. Okay? If they asked us for v initial, we would just rearrange this equation to solve for v initial. But what would we need to solve for v initial? We need to have v final, a, and t. So if we were given 3 of the 4 variables here, we can solve for the last one. And that holds true for any one of these equations, for the second and the third one as well. Now, I'm not going to derive for you the second and third equation. I don't think it's that difficult, but I think for about half of us, we'll need a stronger foundation in math in order to get this done. I mean, basically, it's going to be algebra, combining together equations, substituting in. And so what I'm going to do is I'm going to skip on deriving these particular equations for you. You will get that in physics. For those of you who've had physics already, you probably derived it already. But don't worry about deriving these. You just need to worry about how to use them. Okay. And again, in order to use this equation here, we have, let's count how many variables we have. 1, 2, 3, 4 different variables here. And so if we have 3 of the 4, we can solve for the missing one. Okay. And so t here and t, this represents time. And so down here we have 1, 2, 3, 4 variables here as well. And again, if we're given 3 out of the 4, we can solve for the missing one. What you need to be able to do in these types of problems here is you need to be able to identify what you're given so that you can figure out what you're solving for, okay? And then rearranging any of these equations to solve for your unknown, okay? And so the process then becomes, the process is still the same. The problems become a little bit more complex, but the process is still the same. So please make sure then that you practice using the simple problems first, okay? And then with the more complex problems, then I think you'll be able to work those out. Okay. All right. So with that said, then when we solve for these here, make sure then you understand the acceleration is constant. Okay. Constant meaning then the acceleration doesn't change. 0 acceleration is also constant acceleration. So make sure you keep that in mind. Okay. What we're going to do then is we're going to consider then an average acceleration. So if the acceleration is constant, that means then at every point in time, then the acceleration will also be the same. So instantaneous acceleration and average acceleration will be the same. Okay, and so make sure you keep this in mind, and that this works. We can assume average acceleration because for very short intervals of time, that's going to be true. Okay, that'll be true. So what we're going to do then is we're going to apply with all of these problems, and we're going to assume average acceleration. Okay. All right. So with this particular formula here, what you need to make sure you understand is that this particular formula here gives us then information about velocities, acceleration, and time. What it will not give us then is displacement information. Now, how do the formulas then give us displacement? Okay, again, that's derived, and so we won't be able to do this. But if you saw then, 2 of the kinematic equation has delta x in it. Remember, delta x is displacement. Okay. So we'll get to those formulas hopefully tomorrow. I'm running a little low on timer. We'll get to those tomorrow. What I want to do is I want to focus on this equation here. So this equation here will give us information about velocity. Okay? Velocity initial and velocity final. It will give us information about time, acceleration, and time as well. So those are the 4 variables. Those are the 4 factors that we can obtain from this equation here. So if we're given 3 of the other variables, we can solve for the missing one. So if we were asked to solve for velocity, if we're asked final, if we're asked to solve for velocity initial, if we're asked for acceleration, or if we're asked for time, this would be the ideal equation to use to solve for that. If they ask us to solve for displacement, we cannot use this equation because displacement, remember, displacement is delta x. We describe displacement as delta x. It's not included in this equation. Now, could we use this equation to solve for delta x? Absolutely, but it has to be used in combination with one of the other 2 kinematic equations. And so, like I said, folks, these problems involving kinematics can get fairly complex, but it's not that much more difficult. We just have to make sure then that we approach the problems very methodically. I will not ask you to do the more complex problems here, okay? I will not ask you to do the more complex problems here. You should be able to do the simple ones, okay? And on the practice on the practice assignments that I give you. You'll get a chance to practice that. But the key to starting out these kinematic problems then is identifying what you know, identifying what you're solving for, and then using and identifying the correct formula or formulas later on, and then you'll have to do that later on, that you'll need to solve for your unknown. Okay, so that's going to be the trick. That's going to be something that you have to be able to practice as you go through this. You'll get more practice doing this. So let's go ahead and let's practice this. Okay? And I'm going to practice this with you. Okay? And work these out. Okay. All right, let's do a simple problem here to finish out, folks. Let's do a simple problem here, and I'm going to work this out. And it always is very helpful, folks, to draw a picture. And in physics and in science in general, always draw pictures. That's going to help you as we go through this. Okay, so I'm going to go ahead and draw a real simple picture here, first of all, to help us get through this. Okay, so let's go ahead and let's draw the picture here. Okay, and let's see what we have here. Okay, so we have our car here. So this is our car. And folks, if you're not used to drawing pictures, get in the habit of drawing very simple pictures here. Okay, and we see then that the object, the car is going to move, obviously, because it has an acceleration. So the car accelerates and it gets to some point. Okay, and we'll draw this here. Okay, it gets to some point. Okay, and we're going to measure this in terms of the distance here. We can measure this in terms of time. So this will be time is equal to 0 seconds. Okay. And time here, some time final, you're going to see then, if you recognize it, that that's what they ask you to solve for. Okay. All right. So what do they give us? So let's go ahead and identify what they give us. Okay. So in your diagram, you can include what they give you, and that helps you to visualize this. So they tell us then that we start out, they give us time 0, they give us the acceleration. They tell us then that the object, the car, accelerates at a rate of 5.5 meters per second squared. Okay, so that's the acceleration they give you. Okay, and what else do they give you? Let's go ahead and identify this here, folks. They tell you, hopefully you see then that there is a velocity, or the unit here, it tells you the velocity, but which velocity is this? Okay, well, hopefully you recognize then that they tell us that it accelerates from rest, which means then that's their starting velocity. So over here, rest meaning 0. Okay, so the velocity initial here is going to be 0 meters per second, and at whatever time final here, whatever that time is, it reaches a velocity of 28 meters per second. Okay. So in this diagram here, we have laid out what we know. We know the acceleration. This is constant acceleration, okay, constant non-zero acceleration. We have identified the starting time and the starting velocity, and then we've identified the final velocity here, and finally we have listed then what we need to solve for. Okay. All right, so what formula can we use to solve for this one? Well, we have only had one formula so far, folks, and that is the formula involving v final is equal to v initial plus acceleration times time. Okay, so this is the formula that we will need. We need to rearrange this equation to solve for t final. Okay, so does this equation give us t final? It does not. It doesn't give us time. Okay, that's what we want here. We want time. So what do we have to do? Let's go ahead and rearrange this equation to solve for time. Start out with then, let's subtract v initial from both sides. So we have v final minus v initial is equal to a times t. So we're solving for time then. Divide both sides by acceleration, which is be by a, which is going to be v final minus v initial divided by a. And there it is. This is now the equation that we can use to solve for time. We've isolated time. Okay, and so let's go ahead then. If we're going to solve for time, we need these 3 here. And are we given them? Yes. We go back to our diagram here, and we see that we have been given that time. So let's go ahead and given v final. So let's go ahead and substitute that in. That's going to be 28 meters per second. V initial is going to be 0 meters per second. And then finally, acceleration then we're given is 5.5 meters per second squared. Everything there is what we're given. Plug the numbers into your calculator, and you end up with a number that is 5.1. And real quick, doing the unit analysis here, you're going to see then that everything cancels out. Everything cancels out except for seconds, except for one of these second units here. Okay, so invert multiply here. The meters cancel out. One of the seconds cancel out here, and we have 1 second unit there. And so that ends up being our answer to 2 significant figures. Okay. All right. So with that said, then we'll continue. We'll work out more of these problems tomorrow. Okay, so take a look at this. If you have any questions about this, come by and see me. Okay, stop by and see me, and then we'll talk about it then. Okay. All right. So with that said, then nothing to turn in here today, folks. Make sure then that you just watch the video, work through these problems again on your own. Okay, and then if you have any questions on how we come up with these problems here, make sure you come by and see me. Okay. All right, very good, folks, and I will see you tomorrow.